Good morning, everybody. We're going to wait just another quick minute just to give everyone an opportunity to join in, and then we'll get started. All right. Good morning, everybody. I hope you have had a good week so far. Friday, finally. I'm sure you're all excited for the weekend. So the plan for today, as per usual, we will be going over any questions that you have for the assignments or for the handouts, after which we'll finish up the material from yesterday, and then we'll be going into the material for today. Just a couple of quick things before we get started. One reminder is your situational problem is on Wednesday. This afternoon, I'll be posting a list of topics just to remind you. So that list of topics is going to include the topics from CST and any topics we've covered so far together. So all of those are fair game. Remember that. The list will be posted and will include all the CST topics as well, so you don't have to worry about that, but make sure you're preparing as much as possible over the weekend and over the next few days, making sure you have a decent memory aid. Again, the memory aids are not something that should be left until the night before, so try to get that done over the weekend. Other than that, this afternoon I'm going to post some practice questions, like a mock final. One of the textbooks did, just to remind you that yes, that's going to be important, but the assignments that I'm doing with you, the docs and the forms, those are all exam level questions. So you should be practicing those as well. You shouldn't just be waiting for this like mock practice final and saying, I'm just going to do that, because those are the same level too. So those are questions like you could expect to have there as well. So you really should be doing those. I provided assignment 6 feedback yesterday, and I started assignment 7 feedback this morning, and we'll finish up assignment 7 feedback today and 8 feedback today. And then by the end of the weekend, you'll have 9 and 10 as well. But what I'm noticing is this big trend of people not completing the docs, which means you're not practicing the Part C questions. And we all know how important those Part C questions are. So make sure you're taking the time to complete those assignments and really seeing if you can do them on your own. Because like I've said before, and I'll say it again, it's one thing to understand it when I'm doing a problem. It's another thing to be able to do the problem by yourself. So you need to be making sure you can do that. To answer the question, will we get a practice exam before our C2? That's what I was saying. I was posting practice exam this afternoon for your C2, not for your C1. So those questions that I'm posting will be for the C2. It's very hard to do a practice situational problem because it's just like, it's very situation specific, and it's they're all very different. But the C2, you get you kind of get the gist. After a while, you're doing the same kind of problems and so on and so forth. So that'll be posted early this afternoon, and then we can take a look at those together. And then throughout the week next week. We have a bit lighter week in terms of content. So you can be a little bit relaxed about that, but that also will give us an opportunity to try to cover some of the practice exam questions and stuff like that. So I have some questions already to be going over. So assignment 6, question 1, assignment from yesterday. So assignment 9, question 2 and 3. And while I'm opening that up, if there are any other questions, feel free to post them quickly so we have time to go over them. All right. So I'll try to do them in order. So I see assignment 6, question 1, 2, 3. I'm going to go over 1 for sure, 2 and 3. 3 for sure we covered in class together. So take a look over that one. The solutions are posted as well. I'll take a look at question 1 and 2 very quickly. So this is assignment 6. Question 1. So question 1, you have the picture that you're looking at, and you have to find the rule in symmetric form and in general form. So if we remember, we have symmetric, which is x over a plus y over b equals 1. So I'm looking for the intercepts. So I end up with x over -5 and y over 6, because on the graph, it passes through 6 and -5. So that's where this comes from. And then it says change this to general form. So when I'm changing this to general form, I need to get rid of these. So I'm going to multiply by a number that'll cancel both of those at the same time. So I'll multiply by 30. Now remembering that when I multiply, I'm canceling out the denominators. So 30 times x divided by -5 gives me -6x. 30 times 1 is 30 divided by 6 is 5, and that equals 30. I need to make this positive, so I'm going to move this to this side. And by doing so, I get one side 0, which is the third criteria anyways. And I get 6x minus 5y plus 30, and that's in general form. Number 2. It says, in the Cartesian plane, a theater, a restaurant, and a museum are represented by points TRM. So you need to find the distance from line CR to M. So the first thing we need is rule of CR. So we have points 140 and 100, 200 and 220. So we get our slope is y2 minus y1, 220 over 100 divided by x2 minus x1. Remembering that if you have this in an exam that you're showing your work, but I'm just trying to save us time. So we have 120 over 60, so that's 2. I need to find my b, so I plug in a point. So I get 100 equals 280 plus b. So if I move this over, I get that my b is negative 180. So this is my rule, but I need it in general form. So I have no denominator, so that part's taken care of. So all I have to do is move this over, and I get 0 equals 2x minus y minus 180. So now we're going to be using the distance point to line formula. So we have 0 equals 2x minus y minus 180, and I have point 170/50. So this means my a is 2, my b is negative 1, my c is negative 180, my x is 170, and my y is 50. So all of these go into the formula. So I get 2 times 170 plus negative 1 times 50 minus 180 is the c, all over 2 squared plus negative 1 squared in brackets. It's working the same way as the distance formula, if you remember. So this gives me 340 minus 50 minus 180. And underneath we have the root of 5. So this gives me 110 over the root of 5, giving me a distance of 49.19. And then I just multiply the cost to give me 8608.25. So that's how much that is going to cost. Okay, so that was assignment 6. Assignment 7, question 2. All right. Assignment 7, question 2. Ingrid wants to buy a circular pool so that she can set up a water garden. So you have 2 different functions. Both of them are saying, both of them are giving different pieces of information, and you're told that they're both quadratic functions. So she has her pool. She has the radius of her pool, but you're not given the radius of her pool. You're given the cost at store G. So first and foremost, I need both rules. So rule for G and rule for H. So before I do anything, I'm going to do that. So y equals ax squared. For G, I just pick a point, really doesn't matter which. 144.5 equals a 85 squared. So 85 squared gives me 7225A. And I divide to give me 0.02. So that means the rule for G is y equals 0.02 x squared. We do the same thing for H. So for H, I'm going to choose the second one. I have 376.32 equals A, and I have 112 squared. So if I do 112 squared, I get 12544A, and I divide. So I get 0.03. So I have my two rules. Now I want to figure out what I need to do with them. So we are told that at store G, the cost of her pool would be $544.50. So that's a Y. If I know that it's going to cost this for her pool, I could figure out the radius of her pool. So I'm just going to plug this in here. So then we divide by 0.02. So 544.5 divided by 0.2 gives me 2722.5. No, made a mistake there. 0.02, got it. Just typed it in wrong on my calculator. So we get 27225, and I square root, and that gives me 165. So I know the radius of her pool is 165. Now I need to know how much it's going to cost at pool H. So I'm going to plug in her radius, or at store H. So I'm going to plug in her radius into store H's rule to see what it would cost at store H. So I have 165 squared, which we know is 27225. And then we multiply by 0.03. So the cost at the second store would be $816.75. So this is like a this is a part C question that you could get with quadratic. So you're creating a couple of rules, and then they ask you to use the rule forward and use the rule backwards. So they're essentially testing if you can do this backwards and forwards and if you really understand the rule. Okay, the last thing is yesterday's assignment question 2 and 3. So I'm just going to save these for a second just because we're in the middle of those type of problems. So I just want to take a look at them together before I give you just the answers to the handout. So we'll take a look at that and we'll try to go back to those problems a bit later, okay? So I do want to give you an opportunity to sit down and try them first. All right, so if there are no other questions or concerns, we can get started. So yesterday, we're still finishing up yesterday's notes, and then we'll get started on today's. So yesterday's notes, we started talking about the exponential function. So most of this was review, and it's super important as we remember, or as we, why do I keep doing that? Because the exponential function comes up in itself. I saw your question, can you do 2 and 3 on assignment 9? And I just answered it and said, I'd like to save it until I go over again what we are finishing up for today. And that'll help you do those assignments because we actually haven't finished the material in order to help you do those assignments. So I want to do that first. And then if we have time, we'll go back to it. Okay, so exponential comes up a lot, and you often get a question in exponential, guaranteed. Whether it's A, B, or C, we don't know, but at the end of the day, you'll get one. So we did solving different types of equations. Then we talked about the basic function where you had y equals c to the x, but no one really uses that because we like to introduce more parameters. So we talked about graphing. Then we introduced parameter A, and we talked about the role that parameter A plays. So in terms of a stretch and a compression, that gives us 4 different case scenarios when you put the combination of A either being positive or negative, and C either being bigger than 1 or between 0 and 1. That gives us 4 different pictures, something super handy to put on your memory aid. So do not forget that. We practiced finding the rule just given random points. So when you're finding the rule, you're always identifying the 0 number point because that gives you your A. And once you have your A, you can just use another point to solve for your C. Then we talked about different ways of solving equations. So we had matching bases to help us solve the equation. So we are working, when you're matching bases, you're working with the idea that if I have 2 things that have the same base, if I have 2 to the something equals 2 to the something else, then those somethings must be equal to each other in order to make that mathematically sensical. And then we talked about the tool that you used last year to solve problems, which was guess and check. And we talked about how inefficient that is, especially if you don't have perfect answers. So if it's not exactly 9, if it was 9.38, guessing and checking, you can never get a precise answer. So we talked about the next tool that you're going to use. So the question on the side is, how do you know which tool to use to solve equations? So we're actually just forgetting about guess and check. It's no longer something we're going to be using. So that's kind of out the window. You match bases when, so like this one would be solved by matching bases because you have 2 exponents that are variables. But this one, for instance, could be solved using logs. This one cannot because you have the 2 exponents that are variables. So when you have the 2 exponents that are variables, you have to use matching bases, and any other time you can use the logs. So then we talked about the fact that there has to be a better way to invert an exponent. So then we started talking about the definition of the inverse of an exponent. So we looked at it graphically saying, okay, well, this is what the graph looks like. This is what the graph represents. We have this function. We call it the logarithmic function. It is the inverse of an exponent. It is an exponent itself. It'll allow us to access the exponent. It has an asymptote, and it is a function itself. So like I said, if you go into grade 10, you are in grade 10. If you go into grade 11 TS, then you'll be doing this in more depth. So this is just right now, we're kind of just visually looking at it just to see if we recognize the graph. So one of the questions on your quiz, on the quiz 9, so on the forms, was identifying the graph of a logarithmic function of the inverse of an exponential. So here, if we take a look at that. So this question, you are given the exponential and asked which graph below represents the inverse of function f. So essentially what you're doing is you're trying to identify this picture based on what you understand about exponential functions and what you understand about inverses. So the fact, first of all, you have to recognize the direction of the curve. So you had the 4 different exponential function curves, but now you have to see that, okay, look, this, you remember it's flipping. So this side here, where it's like getting exponentially close to the axis but never touching it, happens down here. And then it curves, and instead of going shooting up, it's like curving slowly upwards. So when you're doing this question, you're essentially, again, identifying, do you understand what this means. So when you have questions like this, I'm just going to go over this question because it's an important one. When you have questions like this, your first goal is to eliminate as many case scenarios as possible. Whoops. All right, I didn't want to answer, but that's okay. So in this case, you're looking for the general shape that we just looked at. This general shape is an exponential function. This general shape is also an exponential function. So immediately I can cancel this one out and cancel this one out because process of elimination says I need the general shape of a logarithmic and not an exponential. So gone, gone. Now, even if I'm really not sure, I have a 50-50 chance of getting it right. But I'm frozen. Like my screen is frozen? No. Guys, do you see the fact that I'm changing from A to B right now? No, how is that possible? So I have the one on the side open and it shows me switching screens right now. So I don't know how I'm frozen. Now I'm not. Okay, my cursor wasn't moving. Okay, so we're good. We're back on track. So we have eliminated A and we have eliminated B. C. So this one and this one, the two on the left. Now we have to understand what we have to analyze what we understand about logarithms and exponentials. And one of the most important things that we understand about logarithms and exponentials is 0, 0 is not a legitimate point for us. So even if it was this one, 0, 0 cannot be a point on an exponential because 0 is an asymptote. Same thing for the logarithmic function. So here, this cannot be a function. This cannot be our logarithmic function. It passes through 0, 0. So the only viable option left for me is B. You can't choose A because you look at the general shape of A, and the general shape of A, if you look at these curves, A has this curve, okay? So A has this curve. And so if you compare, that's the curve of an exponential, not the curve of a logarithm. So we're looking again for the inverse. So we're looking for something that has this general shape. So the two that have this general shape are B and D. So B and D. And we eliminate D because it can't pass through 0, 0. So you have this passing through 0, 0 thing happening here or here at the bottom. So you look at the bottom of D and it passes through 0, 0. And since we can't have that, oh no. There we go. Here, since we cannot have 0, 0 as a point on my logarithmic function, I just eliminate that and we can only choose B. So B is our solution. So we talked about, so we understand that log is the inverse. So we practice just using this relationship to just find the inverse. So we recognized that we have the bases that are the same. and the exponent kind of flips positions. So we just did some practice with inverting them forwards and backwards based on this relationship. So remembering that the exponent will come as the input and the base stays the same. And how this becomes extremely helpful for us is using this relationship, because now all of a sudden this becomes a tool for us to use when we're solving just basic exponential equations. So this is where we left off. We had started to solve some basic exponential equations. So I want to take a look at a couple more just to make sure we're all on the same page before we continue on. So we're going to look at, we'll look at any of them, doesn't really matter. Okay, we'll start here. So the first thing that we do when we're solving equations like this, remember, is that I need to isolate this term. Now, I saw 1 or 2 assignments. Remember that when you have this, it's a barrier. So I cannot put this inside. So I have to divide by -2 in order to figure this out. So you cannot multiply this in. So that gives me 2/3 to the 3x equals, what ends up happening here is I get positive, because the negatives cancel out, 8/27. Once I get to this point, I'm just going to keep scrolling this down so we have it with us to solve our equations. Once we get to this point, we use our relationship because we have this isolated, so we can use our relationship to reverse this. So we have the A is this, so that's going to be on the top. We're making sure we use brackets. We get the exponent that's by itself, and this goes on the bottom. So I type that into my calculator. So 3x is, so I type in log and I use brackets. And I get that this is 3, so I divide by 3, so x is 1. We'll try F. So once again, you need to isolate this term. So the first thing I'm going to do is I'm going to move the 120 over. And then again, I need to divide by 8 because I cannot bring that into the bracket. So 120 divided by 8 gives me 15. Again, using our log relationship. So we're going to be switching it over with this. So we have the exponent is 2x plus 1. That is going to be equal to, I have the 15 that goes on top and the 4 that goes on the bottom. So 2x plus 1, I type that into my calculator, log 15 divided by log of 4. This gives me 1.953. I subtract 1. So that gives me 0.953. And I divide by 2, giving me x equals 0.4767. We'll do this last question here. Again, we're going to do this with, we're about to do word problems with like 5 different types of word problems. No. So when we are using the word problems, we're going to be using this tool to solve different things. I didn't drop the coefficient, I got rid of it. So I moved the 120 over and divided by 8, and that got rid of the coefficient here. You have to get rid of the coefficient. Before you can use this log relationship, you need to have your exponent, like the base exponent term, completely isolated, and then you can switch it. If it's not completely isolated, you're doing something that's not mathematically legitimate. How many numbers after the decimal do you need to put? It's always good form to put at least 3 until your final answer. So try to keep as many as possible until you're absolutely done. Okay, so one last time. Here we have, this is already isolated. So the 3x gets dropped. This is going to go on the top. And the 1/7 goes on the bottom. So that gets typed into your calculator. And it gives me -2.57. And I can divide by 3, which gives me -0.858. So this right here should be on your memory aid, because now that you're expected to know this type of solving, the questions that you would get in an exponential problem will not be guess and checkable. So it's going to be decimal numbers and stuff like that. So you won't be able to just, oh, I'm going to guess and check and spend 2 minutes. Like, you're going to have to use this relationship. So be comfortable with it. And really understand how to use it. It is on the mock memory aid. It's presented a little differently though. So it's right here on the top. So when I give it to you like this, I'm condensing these 2 into 1. So it would be better for you to just put the one I gave you, because this makes it more complicated and it's not as easy to use. So that's why I said this is a good base, but always check through the notes to see if I've done it differently or simplified it for you. And in this case, I've simplified it for you to make your life easier. All right, so that brings us to word problems. So these are the type of word problems that you did during the year with exponential. We're just going to go through a couple of examples quickly before we start the new type of word problems. So we talked about finding the rule from different points, which was fine. Now we're going to be finding the rule from a word problem, which for the most part is actually simpler because I don't have to solve for anything for the most part. Sometimes you do, but rarely. You're basically just taking out important pieces of information from the text that you're given. So your first job is to identify the base. So there are 2 different kinds of bases that you can get. So it's either a factor that you're multiplying by over and over. For instance, doubling, tripling. If it says half-life, it decreases by 2/3. Those are the type of things that you're looking for. And that plugs in as your base. Remembering that we have y equals ac to the x, c being our base. So really, you have to identify the base. The other type of base you have are the percent increase and percent decrease, where it says it decreases by 15% every year, or it increases by 2% every month. So you have these different types of things. So if it says percent increase or percent decrease, it pops in as your base. So this is still going to be your C. But it pops in here as you do 1 plus, if it's percent increase, so I increase by 4% every month, you pop your base in as 1 plus percent over 100. So if it was 4%, this would give you 1 plus 4 over 100 to give you 1.04. And if in this case it was 25%, let's say, you would do 1 minus 25 over 100. So a car depreciates in value 25% every year. And that gives you 0.75. So these will pop in as your base. Other than that, you'll see things like this population of bacteria triples every hour, or something like that. So oftentimes it's population, either of people or of bugs or of insects, lots of gross stuff. And then you'll see a lot of percent increase when you're putting money away in savings accounts, and you'll see a lot of percent decreases because cars depreciate at an exponential rate. So you see those type of problems too. Not people is gross stuff, the bugs and insects. I can see why I said that in a funny way, but I meant the bugs and insects. Personally not a fan, but that's fine. So in order to do these problems, you have to define your variables. Super important to define your variables, especially when we do the other type of problems that we'll do today. You're trying to find the start value. So whatever you set y to be, if y is number of bugs, your a is going to be how many bugs do you start with. Or if your y is the value of a car, your a is what does the car start at. Then you need to identify the base. And then you create your rule, and then you're going to use the rule. So you've done these before. We'll do number 2 and number 3. A car bought at $30,000 loses 20% of its value every year. What is the value of the car in 5 years? And how many years will the car's value be less than 1,000? So step 1 says I identify my variables. So here they say every year. So my X is in years. My Y, we're looking at value of the car in dollars. So you have your rule y equals AC to the X. So A is, what is the value of the car starting at? Well, it's 30,000. You're looking for the base. So in this case, the base you have loses 20%. So that is percent decrease. So I have 1 minus 20 over 100 as my base. So if I put this together, I get 0.8 to the X. Now, once I have my rule, I can start solving for different things. So A says, what is the value of the car in 5 years? So we have X is 5. So we have 30,000, 0.8 to the 5. So I have 0.8 to the 5. And that gives me 0.32768. And I multiply that by 30,000. And that gives me 9,398.30.4. B says, when are we going to hit y equals 1,000? So I plug in 1,000, and this is equal to the 30,000, 0.8 to the X. So I divide by 30,000. How'd I get 5? The question says, what is the value of the car in 5 years? So I'm just doing that part of it. So I have 1,000 divided by 30,000, trying to keep this as a fraction. So now I can use my log relationship. So that allows me to access this x. This will go on the bottom. Base goes on the bottom. And log of 1 over 30, this is on the top. So I just type this in. $15.24. Take that, guessing and checking. 15.24 years. So like I said, these are the type of problems that you handled last year. You just have this added bonus where now you can use this tool to be able to work backwards without having to guess and check. So you don't have to sit there and be like, okay, I'm gonna guess all these things. And even then, like the 0.24 would be very hard to find. So this just allows you to get a very precise answer in a way more efficient way. So from here on out, like I said, these type of problems for this class are going to require you to be using that tool so you won't get perfect answers. How do we feel about this? Okay, fantastic. So what we are going to do now, so there are two other problems you could take a look at if you want to take a look at them. The question before was about assignment 9. So the reason I didn't touch it earlier is because this here is a log question. I really want to see if you can do it. Same thing with this. Isolate the exponent term and then use the log relationship. And this question is an example of a part C exponential function question. So just like the one we just did. So I want to give you time now, not now this minute, but over the next day or so to try these out. And then we can go over them on Monday once you've attempted them. Because like I said, the important thing is to be trying these on your own and not just waiting for me to show you how to do them. All right, so that's the end of the basic exponential function. So there are just two different types of problems for exponential that we have to go over. So we are officially in notes 10. So officially in notes 10. So in all the problems, it said things like every year or every month, every day, every hour, every minute, whatever. But so all of those things mean every 1 minute, every 1 hour, every 1 day, every 1 year. As soon as you change that, if you say every 2 years, every 5 minutes, every 20 minutes, every 6 days, all of a sudden, your rule is going to change because you're not doing this multiplication every unit time. So unit time would mean 1 hour, 1 day. It's not every unit anymore. So somehow we have to account for it not being a unit anymore. So there are two different ways we could look at this. You may have seen this already in your year with parameter b, which is fine. I prefer to use this one because it's a little easier to extract from the problem. So d is the period of time the change is occurring. Okay, so example, 2 years. would mean that D is 2. And every 6 months would mean D would be 6. The problem is B and D have this inverse relationship. So if you're trying to plug in the B, you have to remember to flip it. So if we just do it with D and use this formula, we don't have to worry about flips or anything like that. It just kind of goes in there. So the role, okay, the role that B has is similar to the role of C. So watch what happens. So we know what A does, but watch what happens when I start to play with the B. Okay, look what's happening. And if I go back to 1, the same thing happens when I manipulate C. But we know that A does something different, okay? So when I manipulate B, I'm doing the same thing as manipulating C, even with the flip over here. So B and C kind of play the same role in terms of graphs, but we're dealing with the B more so in terms of word problems and the period of increase or decreasing, switching up. So the first step when you're doing these problems is defining your variables, because it makes a difference if you define it in minutes or in hours, because I could convert those one to another. And my D ends up being different if it's in minutes or if it's in hours. So here, the population of bacteria triples every 3 hours. So if I define my X to be hours, my D is 3, because it's every 3 hours. This is where it gets a little trickier here. So if I define this one here, the population of bacteria triples every 30 minutes, if I define my X to be in minutes, then my D would be 30, right? Because it's every 30 minutes. But if I say my X is going to be in hours, 30 minutes is half an hour. So every half an hour. So in the end, it doesn't matter, because you could do it this way. And as long as when you have an X value, you're plugging it in as minutes, or here if you have an X value, you're plugging it in as hours, it doesn't matter which one of these you choose. The way you use it and the answer you get is the same, but you have to be consistent. As soon as you define this as minutes, everything's done as minutes. As soon as you define this as hours, everything is done in hours. So here, a car loses 5% of its value 4 times a year. So again, I could do this in 2 different ways. If my X is months, 4 times a year is every 3 months, right? Divide the 12 by 4. So that would mean my D would be 3. But if I define this to be years, 4 times a year means every quarter year. So my D would be 1 quarter. So essentially, the only thing that's different now, we're going to be doing a couple of word problems. The only thing that's different now than what you did before is it's going to say every 5 months or every 6 minutes or something. Instead of saying every 1 minute or every 1 year, it's going to say something like this. And you just have to introduce this parameter using this rule. So So let's take a look at what this looks like. Larry bought a car for $25,000. It depreciates in value 8% every 6 months. Find its value after 4 years. So I have to define my variables before I make a move. So do we want to define this in months or in years?
Years.
Any takers? Sure, months. Could you have done in years? Absolutely. Value. Car, dollars. So what do I start at? So my A is going to be 25,000. My C is, this is a percent decrease. So it's going to be 1 minus 8 over 100, which is 0.92. And in this case, my D is every 6 months. This is in months. My D is 6. So when I create my rule, I plug it in, y equals AC to the x divided by D. So I get y equals 25,000, 0.92 to the x over 6. Now, the only thing that gets tricky is I cannot just plug in 4 because 4 is years. So 4 years equals 48 months. So I have to plug in a months now, which is fine. Doesn't really matter. So I get 25,000, 0.92, and I get it to the 8. So you can type that in. So I get 12830.47 dollars. So notice the whole problem is the same except for this step right here and this right here, which just adds an extra step here. Makes no difference. If you had decided to do this in years, I'll show you how this would change. So if your X was in years, Y is still value of car. Your A doesn't change. Your C doesn't change, but your D does. So every 6 months is half a year. So you have your Y equals AC to the X divided by D. So you'd get Y equals 25,000, 0.92 to the X divided by a half. So then I would plug in my X equals 4 years, which I can do now because I've defined this as years. 4 divided by a half, or 4 divided by, if you prefer, here, 0.5. So 4 divided by 0.5 gives me to the power of 8. And when I type this in, I get the exact same answer. So like I said, when you get into it, does it matter if you define it in years or in months? Absolutely not, as long as you are consistent throughout your problem. So if you start in years, you work in years. You start in months, you work in months, period. All right. Okay, let's do number 3. A population of deer, 1,500 deers, increases 15% every 2 years. I'm going to use years. And dun, 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 dun. This will be number of deer. I have a question that says on the side, can we do one on our own? What I'll do now is I'll leave you 2 minutes. 2 minutes, create the rule for 2, 3, and 4. You don't have to answer the question, just make the rule. Essentially, just get to this point for those 3, and then we'll check the rules together, and then we'll just do a couple of calculations. So you have 2 minutes. Check that out. Okay, let's take a quick look at these together. So we'll just create the rule for them, and we'll do 1 or 2 of the calculations. So in number 2, we'll create the rule. So a $5,000 investment increases by 2% 4 times a year. So if I'm talking years and dollars, my A, it starts at 5,000. My C is going to be 1 plus 2 over 100, which gives me 1.02. And my B, 4 times a year means a fourth of a year. Sorry, my D, not B. So 4 times a year means a quarter of a year. So Y equals 5,000, 1.02. This you can write as 0.25. So you'd get X divided by 0.25. So then it says, we'll do the calculation for this one. It says, find out how long it will take for the investment to reach 7,000. So I plug in 7,000. And I'm going to solve. So first I divide by 5. So 7,000 divided by 5,000 gives me 1.4. Now this is where my log relationship comes in very handy. So this switches up. I get x over 0.25 equals, this goes on the top, log of 1.4 divided by log of 1.02. So log of 1.4 divided by log of 1.02 gives me 16.99. And I bring this up. So that means it's going to take 4.25 years. Can everyone hear me? Okay. So yeah, in months, so the rule just quickly in months would have ended up being y equals 5,000, 1.02 to the x divided by 3. So yeah, you would have gotten 51 months. Does that make sense? So we'll just create the rules for the other two. So here we have the population of deer increases 15% every 2 years. So here I start with 1,500. My C is going to be 1 plus 15 over 100, which gives me 1.15. And my D, it says every 2 years, so the D is 2. So you get 1,500, 1.15 to the X divided by 2. So we'll just quickly do this one. 8023 equals 1,500, 1.15 X over 2. So if I divide by 1,500, I get 5.349. Switching this up with logs. So we have log of that divided by log of 1.15. X over 2 is 12. So X is 24 years. So we'll just create the rule of the last one, just to make sure we all understand parameter B, and then we'll get going. A jar containing 200 insects. In a jar containing 200 insects, the number of insects doubles every 3 days. X equals days. You're not going to convert this to hours. That makes no sense. Well, I mean, you can do it, but it just makes your life really difficult. Number of insects. I wouldn't want that jar anywhere near me. A is 200. C is doubles 2. And D is going to be every 3 days, so D is 3. So Y equals 200, 2 to the X divided by 3. How do we feel about two different things right now? The use of log to solve problems and the parameter parameter D. So it's not too bad. Okay. So like I said, you're going to get, I don't know, but you should get an exponential problem. And now you just have this added D and you have the added method of solving. So everything else doesn't change, but you have these extra things that you can use and that you have to use. So the assignment for today has that stuff in it. There's just one last thing with exponential. It's not as likely to come up, but sometimes it does. It's just one last type of problem, okay? So we'll take a look at it. It's called compound interest. So these problems always say the word compound or compounded. So do not use this unless do not use this formula unless you see the word compounded. Okay? So what this formula is, it's going to say you invest money. It's always money. So these are for compound interest of money. So it's always going to say your starting amount in dollars. Your N is going to be the amount of times the interest is calculated per year, or that is compounded, not calculated. And R is the interest rate per year. So it's going to say the problem will look like this. What this represents in a real life situation is sometimes you get an annual interest rate. They say like 10% per year, but that doesn't mean they only do the calculation once. They could give you interest 4 times a year or 6 times a year, but it's not 6% 6 times. It would be 6%, 1% 6 times to give you the total of 6. I'm not saying you don't have to worry about it. I'm saying it does come up sometimes. It's more rare, but you have to be prepared because they could do this. So just in case we're going over this. And literally the only time that you use this formula is if you see this word. If you don't see that word, that formula doesn't exist to you. So Susan invests $15,000 at 6% annual interest rate, compounded quarterly. So you see the word compounded, and all of a sudden, this is the only formula that exists to you. So from what we just did, A is what we start at, 15,000. N is the amount of times the interest is compounded per year. So if it's compounded quarterly, it's compounded 4 times a year. And the annual interest rate is 6%. So we're talking X is years, always years. Y is money. So I use this rule, y equals a, 1 plus r over n to the nx. As soon as you see compounded, this is the formula you use. Other than that, you never, ever, ever use this. So I have 15,000, 1 plus 6 over 4 to the 4x. This percent should be written as a decimal though. So when you do this, you get 1 plus 0.015 to the 4x. So you get 1.015 to the 4x. And now all of a sudden you have a rule that you know how to work with. So the only difference is you're creating your rule differently, but once you've created your rule, it's the exact same type of rule and you're solving it the same way. Find the amount of money she has after 5 years. So x is 5. And B says, well, we'll do x first. We'll do A first. So y is 15,000, 1.015 to the 4, and we're plugging in 5. So we have 1.015 to the 20. So that gives us 1.3468, and we multiply by 15,000. That gives me 20,202.83 $. B says, how long will it take for her to double her money? Well, she started at 15,000. Double is 30. So I plug in y is 30. I divide by 15,000. That gives me 2. Again, now we get to this point where I could solve this using logs. So I have 4x equals log of 2 divided by log of 1.015. Base always goes on the bottom. So log of 2 divided by log of 1.015 gives me 46.56, and I divide by 4, gives me 11.64 years. So there are 3 more problems, but all we're going to do is we're going to create the rule. Because like I just showed you, once the rule's created, the calculations and everything you do with the rule is the same. It's just that this is a specific way of creating a rule that's different if you see compound interest. So let's just practice creating the rule, and then you can try the other, like to actually solve the problems on your own. Or we'll do at least one more together. Two, the island of Madagascar was sold in the year 1618 for the equivalent of $21. If that amount had been invested at 3% per annum, meaning this means per year, compounded. There's our kicker. Is question 2 true? It is my understanding, yes, but we could Google that after just to verify. Be interesting, right? Okay. Compounded monthly. X is still years, not months. That's the idea with compound interest, is your X is always years. So you have your starting value, $21. You have your base, 3%, or you don't even have your base. We're not even bothering with this. We're skipping straight to the rule. Y equals A, 1 plus R over N, NX. So you have your A is 21. Your R is the interest rate per year. We're going to put it as a decimal. And the N is how many times it's being compounded per year. Monthly means 12 times a year. So we get 21, 1 plus 0.03 divided by 12, and 12x. So I manipulate this equation. So here I get 1.0025 to the 12x. So if we figure out the years here, we're talking 404 years. So that gives us 484. So in 404 years, it would have increased to $70. Not very much. Okay, so we'll create the equation for 3 and for 4. Did I put 484? Yeah, it's supposed to be 4848. Which is going to change this a little bit. Yeah, it changes that quite a little bit. There we go. That's quite a bit of money. Not $70. It's like 3,800,000 more than $70, but anyways. All right, thank you for that catch. Here, John invests $3,500. Doesn't matter. X is years. Y is dollars. A, R, N. You see the word compounded. This is the formula we're using. So A is 3,500. My R is the interest rate per year. So this gives me 0.045. Compounded bi-yearly. Bi-yearly means twice a year. So Y is A, 1 plus R over N to the NX. So this is 3,500, 1 plus 0.045 divided by 2 with the exponent of 2. So this gives me 1.0225. And here's my rule. So once you have this rule, you can just answer the questions like you used to. How long will it take for his money to double? How much money will he have after 12 years? Whatever those questions are, that's what you'll be able to answer now. In this question, it says, Bill Gates wants to invest $16 million for a period of 11 years. He has two options to choose from. Give the amount he will have after 11 years in both cases. So this is more of a type of part C question that you could get. So you have two different options. We're going to put X as years and Y as dollars for both. In this one, it says annual interest rate paid once per year. So in that case, my A is 12, it's 11 million or 12 million? 16 million. Secret option number 3. My C is going to be 1 plus 6.75 divided by 100, which gives me 1.0675. And the D, it says once per year. So this rule goes like this. This situation doesn't say the word compounded, so I do this as normal. This one says compounded. So now I have to use my A, R, and N. A is still 16 million. The R, it's per year, 6.5, but I plugged that in as 0.065. And N says compounded monthly, so that's 12 times a year. So annoying. In this case, you just put it together. So Y equals A, 1 plus R over N to the NX. So I have 16 million. 1 plus 0.065 over 12 to the 12x. Here I get 1.005416. And there's my rule. So remember that you only use this if you see the word compounded. So even if you have interest rate, you've done those type of problems before. You just do this as normal. The only time you switch this up is if you see the word compounded. So I don't want to see, if you get this on the exam, if it doesn't say the word compounded, I don't want to see you doing this. It'll make me sad. Only use this if you see the word compounded. Clear? So that is the end of the exponential function. And now the fun stuff starts. Any last minute questions on that? Cool. Probability. So we are starting probability today. We are going to be doing probability on Monday. We're going to be doing probability on Tuesday. Just to go back to answer the question, what was the formula for option 1? The formula for option 1 was our normal. was the normal y equals ac to the x, because it didn't say compounded. So I did this as normal. This one said compounded. So I did it with the compounded formula.
Miss, is the stuff that we do on Monday and Tuesday gonna be on the situational problem?
Probability. In CST, you don't touch probability at all. Here we do a lot of probability. So like I said, we're going to be doing probability today, Monday and Tuesday, finishing off with statistics on Thursday. And then exam review on the Friday. So we're going to start the probability. Most of this should be review because you do probability in Sec 1, Sec 2, and Sec 3. So it's just not a review of Sec 4. So you don't touch it in the CST class in Sec 4, but you do it in 1, 2, and 3. I'm going to be posting a list this afternoon of what's going to be on the, like, not what's going to be on. I'm not going to give you like one, this is it, this is it, this is it, this is it for the situational problem, but I'm going to give you a list of all relevant topics. So anything that's fair game will be on that list. Okay? So, terminology, a random experiment is an experiment that you cannot predict the outcome of. So these are all the experiments that you see. Flipping a coin, rolling a die, picking a card out of a deck. So you have no idea when you reach into the deck which card you're going to pick out or what die you're going to roll. Before I continue, the question is, how many students usually pass the TS Bridge course? I can't answer that because it has absolutely nothing to do with like statistics in terms of how many people normally pass. It's each individual and how each individual prepares for their exam. So you could have 1 year where everybody passes and the next year a lot of people fail. Like it really depends on you. It depends on your willingness to prepare yourself for this exam. It's like how prepared you are, how much you've been following, how many examples you've done. Like I've stressed this 4, 5, 6 times. The more examples, the more assignments, the more of the handouts that you're doing, the easier this stuff will be for you. And the other thing not to forget is that you do have a lot of CST material that's covered in the exam. So in theory, you should be backed up by that material, right? Like you could get, when we look at statistics and we look at, you know, the scatter plot, you get that in, like your teacher probably prepped you for that kind of part B question where they give you the scatter plot and they say estimate the correlation coefficient. That could come up in this course too. So that could be a question on the final. So in theory, that's something that you knew how to do during the year and you should be able to handle for your final. So there's a lot of CST material that will come up as questions on their own. But that doesn't mean that you can ignore this material either. So it's really all about how much you prepare for this. The comment is, I talked to a friend who was in TS and he said he didn't learn symmetry form. You're supposed to learn symmetrical form in TS and in SN. So in TS, you are supposed to cover symmetrical form. The only one you're not supposed to cover symmetrical form is CST. Okie dokie. So a random experiment is an experiment that you cannot predict the outcome of. So the rolling the die, the picking a card, the flipping a coin, like I know it could be heads or tails, but I have no idea from one flip to the other whether it's going to be heads or tails. So it's random. We call the universal set the list of all possible outcomes in an experiment. We denote this by this symbol, which is a Greek letter for omega. So math borrowed a whole bunch of the Greek alphabet to represent different things. Omega is one of them. For instance, rolling a die, if we're doing the universal set, we write it like this. What are all the different possibilities I can have when rolling a die? 1, 2, 3, 4, 5, and 6. So that is all the possible outcomes in an experiment. So for that experiment, if we did flipping a coin, my omega would be heads and tails. That's all I can get. An event is a subset of the outcomes of an experiment. So it could be one single outcome, or it could be a combo of a whole bunch of different outcomes. For instance, if we're still going back to the rolling a die, event A could be rolling an even number. So we would say A is 2, 4, and 6. What if the coin lands on its side, like through a crack? We're not considering that case scenario. Event B, this would be C. I can't have two event Bs, that's silly. Event B, rolling a prime number. So depending on your definition of prime and what you learned, we're looking here at 2, 3, 5, or 1, 2, 3, 5. Some of you would have been taught to include one. Some of you would have been taught to exclude one. So no, events are specific subsets. So we're talking about subsets. Event C, rolling a number less than 7, is 1, 2, 3, 4, 5, 6. That's still an event because I'm still looking for something. So that brings us to two different definitions: certain event and an impossible event. So a certain event will occur with 100% certainty, like no matter what happens, I'll pull out a card like that, or I'll roll that number. And an impossible event can never happen. For instance, if we say event A is rolling a number less than 7, which we just saw is 1, 2, 3, 4, 5, 6, no matter what I roll, event A is going to happen because all of the numbers are less than 7. So that's a certain event. Rolling a multiple of 8, so if we remember multiples of 8 are like 8, 16, 24, 32, ... That's impossible because no matter what I roll, I'll never get a multiple of 8. Just a quick review of secondary 3 geometry. Geometric probability. So for geometric probability, you had 3 different case scenarios: in 1 dimension, in 2 dimension, and in 3 dimensions. Whoops. So in 1 dimension, it was basically you had a given line or a segment, and you had a subset of the line, so like a certain part of the line blocked off. And if you have like a pointer going over the line, what is the probability of landing on a certain point or in a certain range of the line? So you would, what this looks like is if I had this line AB and I had this little part of it, and we can call this C and D. So if I'm flipping a pointer back and forth and I just randomly stop the pointer, What is the probability that I landed in the red? Well, it's the length of the red over the total. So this would be length of CD over the total, which would be the length of AB. You did a lot of two-dimensional area probability. So you have like a shape like this, and you'd say, okay, what is the probability of landing in the shaded region, or what's the probability of landing in the white region? So we take the area that we want over the total area. And that's the probability that I'll land in that specific place. For 3 dimensions, it's the same idea. You have a volume inside a volume. What is the probability that I land in a certain region or a certain portion of a big shape? So if we look at this, find the probability of landing in the shaded section. So circle, so area, we're just going to quickly do this. So 400. So I get 1, 2, 5, 6. The square area is 81. And the triangle would be 3 times 2 divided by 2, which is 3. You didn't go over circles this year. So if we, yeah, it's prior knowledge. You just need to put like area of circle on there. That's all you'd ever really need. So if I want the probability of shaded, I need the area of shaded over the total area. So the area of shaded is going to be circle minus square plus triangle over the area of the circle. So that would give me 1, 2, 5, 6 minus 81 plus 3 over 1, 2, 5, 6. So that gives me 1178 over 1, 2, 5, 6. So that just reduces to 589 over 628. So that's just the probability of landing in the shaded. So you did that in secondary 3. You had a lot of geometric probability things that you looked at. This is stuff that you learned or should have seen in like secondary 2-ish. So arrangements and combinations. In an experiment that requires several steps, if the first step can be performed in a number of ways, in A ways, and the second in B, etc., the number of outcomes is the outcomes for step 1, for step 2, for step 3, and we're multiplying them. So this is a combination kind of situation. So how many different ways can we combine a menu that has 3 appetizers, entrees, 4 entrees, and 5 desserts? So I take the step 1 would be choosing an appetizer. So I would have 3 different appetizers I can choose from. Step 2 would be entrees. So I have 4 entrees. Step 3 would be desserts. So I have 5 desserts. And I multiply them, that gives me 16 combinations. 60. I think I said 16, but I really meant 60, like what I wrote down. So we're gonna leave it here. The assignment for today has 1 question. The forms has 1 question on probability and the docs has 1 question on probability. You can save those for Monday. We didn't quite get to that part of it. Today, I'm going to be providing feedback for assignment 7 and for assignment 8. Over the weekend, I'll do assignment 9, but I'll save assignment 10 for like Tuesday when you've had a chance to look at the probability stuff. And then I'll be trying to provide feedback ASAP. Make sure this weekend you're working on your memory aid. Look out for this afternoon for that list that I'll be posting and for the practice finals that I'll be posting. And of course, throughout the weekend, look for the notes for Monday and any new handouts or anything like that. If you do an assignment late, do I still correct it? Yes, because as long as you hit turn in, I get a notification that you turned it in late, and then I can still see that it's done. So I just go in and check it. So even if like you look at assignment 4 and you're like, ooh, I really want to get feedback on that, do it and then send it to me and I'll give you feedback. Maybe not as quickly, but I definitely will get to it whenever I can get to it. I try to answer the emails as quickly as possible. But if there are no other questions, have a great weekend filled with memory aid studying and some non-math time. And if you have any questions between now and then, just send me an email. Otherwise, I will see you all on Monday.
Thank you.
Thank you.
Thank you.